Start the recording. All right, now, the last video, we covered the first 4 sections of the probability book, and we're going to cover the last two that I will cover, which is 6.5 and 6.6, and then we'll spend a little time on some of the types of questions that will show up for probability. Now, starting on Wednesday, we're going to go into chapter 7, and what we're going to cover for the rest of the course assumes that you know probability pretty well, but doesn't require you to have an extensive knowledge of it. So this chapter that we're in right now gives a pretty extensive treatment of probability, not a whole semester's worth, but a fairly good treatment of it. So what I'm going to do is, because there is so many different types of questions or problems that could show up on a test for chapter 6, I'm going to show to you the questions that could show up on the test. In other words, I will select from the ones that I will show you that will show up on the test. So if I show you, let's say, 10 or 12 different types of probability questions that I'm selecting from the exercises, the ones that will show up on the test will be one of those. Will be, let's say, if I select 3 or 4 of them out of the 12, those 3 or 4 will come from that list with just the numbers changed. You know, the types of, you know, the numbers and the context of the problem may be different, but it'll be the same type of problem. So you'll know what to study for. Because again, this is not a probability course. It's a course that's preparing you to use probability to understand statistical concepts. And so I will select those for you so you know what to study for. There won't be any issues with that. And that way you'll have you won't be wasting time on things that will never show up. Now, many times in statistics, you'll be presented with a table that looks like this. Now, the table could have counts of people, or it could have relative frequencies. These are relative frequencies here that are inside the table. How do I know what the relative frequencies? Because they all add up to 1. Remember, relative frequencies add up to 1. So you take your count and divide by the total number of people that are surveyed, and you get your relative frequency. So what is this table showing here? Well, in this table here, they're breaking up mortgages. Mortgages, of course, are loans given to people who are buying a house. So they don't buy, you know, they don't use 100% of their cash to buy the house. They're going to take out a loan for most of the cost of the house. And according to this table, there are, in general, 2 types of mortgages in the way you pay back the interest. There's called adjustable rate mortgages and fixed rate mortgages. The adjustable rate mortgages would mean that the interest rate will vary based on the level of interest rates in the general economy. The fixed rate mortgage means that the interest rate is fixed at the time that you get the mortgage and never changes. All right. Now, why would there be 2 types? I mean, this has nothing to do with statistics, but I'll just explain it to you since you might have to take out a mortgage someday. The reason there's 2 types is because if interest rates are, let's say, are increasing, and then you may want to go with the fixed rate, which is currently at a low rate, which is the way it is in the economy right now. The mortgages are very low rates. So if you're going to buy or take out a loan or a mortgage for your house, new house, then you would probably go with the fixed rate because you want to lock in the low rate in case the rates go up. The adjustable rates are usually for situations where interest rates are going down, so that you don't want to be stuck with a high rate fixed mortgage, and you may go with the adjustable rate so that the rate may go down if the rates keep going down. So that's the reason why there's 2 types here. Then there's different types of houses that you may, or living spaces that you may take out a mortgage for. You may have a single family home. You may have a condominium. That's usually for people maybe who are a little bit older. You may even have a multifamily home. Well, there's aren't as common. But these are three types of homes that you may take out a mortgage in. According to this table, for example, out of all the people who took out mortgages, 40% of them took out an adjustable rate mortgage for single family home. That's how you read it. There's a row and a column, right? So the row adjustable and the column single family means the intersection of that row and column, that's the number that applies to adjustable rate mortgages for single family homes. Fixed rate mortgages for condos is in the middle here. You go to the fixed rate row, the condo column, and the 0.09 or the 9% represents 9% of the mortgages are fixed rate for condominiums. So these 6 numbers in the middle here that are represented in the middle here are called joint probabilities, or joint probabilities. I think we will go with that term, joint probability, because they are combining the columns and the rows. They're combining the different types together. And so if we have 2 variables here, one variable is the type of mortgage, the other variable is the type of house or living space that you're going into, then the intersection of those two are these numbers in the middle. So these are joint probabilities. Now, if you needed to total the columns and total the rows, these would be called marginal probabilities. Marginal, because they're in the margins. So if the column totals are the marginal totals for the columns, and then you have your row totals, the row probabilities for the different types of mortgages. Notice that if you add up these 3 column totals, it comes out to 1, and if you add up the 2 row totals, it adds up to 1. All right. So many times these tables will have relative frequencies in here, which relative frequency and probability, you could say, mean the same thing in this case. Or you can actually have the actual frequencies. You could have the actual counts here. So you could have the total number of people in the study that had adjustable single-family homes, had adjustable mortgages for single-family homes. So instead of the 0.4 here, you would actually see the actual number of people. And then this down here, this 1 would be replaced with the total number of people for this entire study. All right. So this is the type of table that you might see. Now, the concept last time, we brought up the concept of what's called a conditional probability. Now, many times we'll want to know the conditional probability because we're only interested in a subgroup of the total number of people in the study. For example, if we go back to this table here, we may be interested in only single-family homes. We're not interested in condominiums. We're not interested in multifamily homes. We're interested in this column here. Or we may be interested in just fixed-rate mortgages. So we may be interested in just this row here. So that's why we have this concept of conditional probabilities. So here we're defining events here. Remember, we use capital letters to define an event. Event E is the event that a mortgage is adjustable rate, and event F is the event that the mortgage is for a single family house. Now, you might say, well, what about the fixed rate? Why don't we have an event letter for the fixed rate? Well, because there's only 2 possibilities for, let's look at them again. There's only 2 types of mortgages, fixed and adjustable. We can say that the fixed rate is the complement of E. It's the E with the C, superscribed C, which would mean not E. So any mortgage that is not adjustable rate would be fixed rate. Okay. Now here they're saying what the event F is the event that the mortgage is for single family home. Now, since there are 3 types of homes here, you probably would want to know, if we were going to look at the other, all 3 of these, we would probably want a symbol for condos or multifamily, and then we probably want them for all three of them because there's three of them. But in this case, we're just having symbols or letters for one of them, which is for single family. Now, the probability, we're given the probability here that the probability of a adjustable rate mortgage is 0.7. How do we know that? Well, actually, oh, this is weird. Yes. How do we know that? Because the marginal total for the adjustable row is 0.7. You see it here. The probability that if you select one of these mortgages at random from the population, the probability that its adjustable rate is 0.7. All right, it's the marginal total here. Everybody clear about that? So I said, you look at this table and I want to know if I wanted you to tell me what's the probability of an adjustable rate mortgage, the answer is 0.7. What's the probability of fixed rate mortgage? 0.3. What's the probability that the mortgage is for a single family home? 0.5. What's the probability it's for a condo? 0.3. What's the probability it's for a multifamily home? 0.2. All right. These are the marginal totals. That's what they're giving you here. Now, what they're asking here is, what's the probability that E given F? Now, what does that mean in words? Probability of E given F. E is the event that the mortgage is adjustable rate. F is the event that the mortgage is just single family home. What if we know, what if you select a person at random and we know for a fact that they purchased a single family house? That is the information that we're given. What we're asking here, what's the probability of the person having a adjustable rate mortgage, given that we know that they have a single family, they've used a mortgage for a single family house? Well, this is the formula for it. It's the probability of E and F, E intersect F, divided by the probability of F. So it's the probability of the intersection of the two, E and F, divided by the probability of that which we know, which is the probability of F. Well, the probability of E and F, how do we know that? What's the probability of that the mortgage is adjustable rate and for a single family home? Go back. Adjustable rate in single family homes, the intersection of this row, adjustable row, and the single family column, 0.4. Right, so 0.4 is the probability of both of those. And then the probability of F is the probability that it's for a single family home. Well, that's 0.5. That's this column right here. Okay. What's the answer? 0.80. It's an 80% chance that if the person has a single family house, they took out an adjustable rate mortgage. Any questions about that? So it's very helpful to be able to look at a conditional probability like this, and be able to say it in words in a practical situation, instead of just looking at symbols and looking at the formula and memorizing the formula. All right. The formula is necessary to know, but obviously, your tests and everything you're going to be doing is open book, so you don't have to memorize this. You just need to be familiar with it. The only thing that you need to be able to do is to apply it to come up with the answer. Here's another one. This is actually in reverse here. What's the probability of F given E? What are they asking for here? Let's go back to what F and E is. They're asking, what's the probability that a mortgage is for a single family home, given that we know that that mortgage is adjustable rate? So in other words, we're selecting a person at random, and we know that person took out an adjustable rate mortgage. What's the probability that it's for a single family house? So it's a different question. Notice the numerator is exactly the same. It's the probability of E and F. It's exactly the same place as in the table here. This here, 0.4, but notice that the denominator is different. 0.7, because what we now know is that the probability of what E is. That's what we know. What is E again? We know that it's for a single family house. What's the probability of single family house? 0.5. Okay. Yes, 0.5. So, no, I think the denominator is E. So we know that the mortgage is adjustable rate. So let's go back. 0.7. That's our denominator now. 0.7. Because we know the mortgage is adjustable rate. So our denominator is going to be E. Whatever it comes out after that vertical bar, that's our denominator probability. So it's 0.4 divided by 0.7, 0.571. Now they make a point here. This is something, let's go back to the previous one, the previous problem we did. We got an answer of 0.8. I didn't mention anything here about this, but look, let's look at this probability here. It's 0.571 is the probability that if we know that it's adjustable rate, what's the probability that's a single family home? What's the probability for a single family home without any knowledge whether it's adjustable rate or not? It's 0.5. How do we know that? Let's go back to the table. Probability of a single family home is 0.5. That's without any knowledge whether it's adjustable rate or fixed. It's just the marginal probability of a single family home. No, and that's called an unconditional probability. There's no information about anything about the type of mortgage. All right, just that the mortgage is for a single family home. So we know that's 0.5. Notice the probability changes when we know that it's for that the E here, we know that it's adjustable rate, right? We know that it's adjustable rate. Notice it increases the probability of it being what? Of it being for a single family home. Knowing that it's adjustable rate, the probability goes up. It goes from 0.5 to 0.571. What is that telling you? It's telling you that in this case, the probability of F, all right, is dependent on, in this case, the information about E. The probability of what? The probability of, let's look at these again. What's E again? Go back. E again is adjustable rate. So the probability that a mortgage is for a single family house is dependent on, will change based on this information that it's adjustable rate. It's going to change. And that's exactly what happened. It went from 0.5 without that information to 0.571. It actually increased the probability based on the knowledge that it's for adjustable rate mortgage. All right? We're saying that the two events are dependent on one another. Dependent meaning that one event will change based on the knowledge of the other event. They are dependent on one another. Now, in statistics in general, what we are looking for when we do statistical procedures in the future is that the events are independent of one another. So what does independent mean? Independent means is that when we do this calculation, that the probability doesn't change. In other words, if we had done this calculation, this conditional calculation, and if we ended up with an answer of 0.5, and it would have matched the probability of this event of a single family home, if the information about adjustable rate had not changed the probability, we would say that E and F are independent of one another. Independent meaning that the knowledge of the other event does not change the probability of the event that we're looking at. It doesn't change it. A silly example would be, let's say you wanted to know the probability that it's going to rain, all right? So you think to yourself, all right, I think you're just guessing at it. There's a 30% chance that it's going to rain. And then you look outside and you see somebody walking their dog. Well, walking the dog, that information about the person walking the dog says nothing about the probability of it going to rain. So when you see the person walking the dog, you think to yourself, well, I still think it's a 30% chance of it going to rain later. In other words, walking the dog, the event of walking the dog has nothing to do with the event of whether it's going to rain. Those two events are considered independent of one another. Knowledge of one does not affect the probability of the other. In this case, these two events are independent because the probabilities are different. I hope I made some sense of that. All right, here's another one here. Here's another event that a mortgage is for a condominium. Go back to the in here. So we're now dealing with this column here. What's the probability that a person took out a mortgage for a condo? 30%. That's the marginal total for this column for condos. Okay, what if we wanted to know what's the probability of E, that we have an adjustable rate mortgage, given that we know that the person has a condo? All right, well, we use the formula again. What's the probability of that E, person has adjustable rate and has a condo? How do we find that? All right, adjustable rate and a condo is the intersection of this row, adjustable rate and the condo, 0.21. And the probability of a condo, which we know is 0.3, we come out to 0.7. 0.7 is the probability of adjustable rate mortgage, given that we know it's for a condo. What is the probability of an adjustable rate mortgage again? Let's go back. 0.7. All right, take a look at this. 0.7. Did the knowledge of it being condo change that probability? What's the answer? Yes or no? Did it change it?
No.
No. So are events E and C independent or dependent?
Independent.
Independent. The knowledge of C, the knowledge that the mortgage for a condo did not change the probability that we had an adjustable rate mortgage. It's the same probability. The probability of E is equal to the probability of E given C. All right. So if the conditional probability is the same as the unconditional probability or marginal probability, then we say those two events are independent. And this is again the case right here. All right. Not this is different than the one previous problem, right? The previous one that we were looking at. Look at this problem here. E and F are dependent because the probability of F is not equal to the probability of F given E. Here, the probability of E and the probability of E given C are the same. Therefore, they are independent of one another. And that is what we're looking for, see, right here? We're looking for this type of a relationship when we are using statistical procedures that we're going to learn later. This idea of independence is extremely important for statistics. This particular section here is teaching you what it means. That's all, what it means. Now, this is a definition. Two events, E and F, are independent if the probability of E given F is equal to the probability of E. Notice if we switch the conditional probability around, in other words, we say, what's the probability of F given that we know about E? Notice that this would also be true if this is true. All right? These two have to be true. If two events are independent, then this is true. This one here, probability of E given F is equal to probability of E. And also the reverse here, the probability of F given E is equal to probability of F. Both of those have to be true for the event to be independent. And they will, if one is true, the other one's going to be true. And that's the definition of independence. Now, if two events are not independent, they are considered dependent. And that means this statement here would have a not equal to here. If they are dependent, the probability of that E given F will not be equal to the probability of E. And if they're dependent, this would also be the probability of F given E would not be equal to the probability of F. All right, so that is something that is important and will be tested on in test number 2 and the final exam. I consider it very important. Now, what's interesting about independence is that you can also look at it with these complements, these not E and not F. For example, what's the probability of not E given knowledge of F? If E and F are independent, then not E and F are also independent. All right, that's the whole idea. If E and F are independent, then not E and F are independent. not F and E are independent, and not E and not F are independent. All right. Sounds kind of funny to say that, but that's what it means. Now, it'll come in handy when we do some problem solving with independence. Now, in addition to this formula, this is the general formula for conditional probability. Right? This is something you need to also know. You need to know this, right? The probability E given F is equal to this ratio of these two probabilities. Notice we can do a little algebra here and multiply both sides by the probability of F. And we end up with this. And what is this, by the way? This is a multiplication rule. We're saying the following: the probability of E and F, or intersect F, is the conditional probability of E given F times the probability of F. Okay. By the way, we could also, I mean, just if we're going to do this, I guess they don't show that here. We could also say the probability of F given E, it has the same numerator, and the denominator would be the probability of E. So the probability of F given E, the only thing changes is the denominator. So if we took that and multiplied both sides by the denominator, we would get the same thing on the left here, the probability of E and F, but on the right, we would get the probability of F given E times the probability of E. You should try that on your own. In other words, look at the formula for the probability of F given E. It's the same thing as the numerator is the same. The denominator would be the probability of E. Multiply both sides, and you'll see you'll have another formula for this, the left side of this. Now, since if E and F are independent, since the probability of E given F is the same as the probability of E, these two are equal, we can replace this right side of the formula here, replace the probability of E given F with the probability of E. They're equal to each other. And we get this very simple formula. What is this formula saying? That if two events are independent, then the probability of them both occurring together or in sequence, probability of E and F, is simply the product of their individual probabilities. If they are dependent, you have to use this formula in the middle here. But if they're independent, we simply say they're the product of their probabilities. Makes it easy, right? And here's the multiplication rule for two independent events. This is only true if they're independent. If they're not independent, the formula in the middle here is the one we use. So if they are independent, we simply multiply their individual probabilities. The key here is we're saying the probability of E and F, this intersect symbol means and. Whenever we use the word and, we're going to multiply the probabilities if they are independent. And then they give an example right here. So it's a long example, and it's a genetic example. I'm going to skip that. It's a little complicated. But let's extend this a little more, all right? The concept of independence also extends to more than two events. We have, let's say, three events. We want to know what's the probability of these three events, and let's say each of these events, each pair of these events are independent of one another. In other words, E1 is independent of E2, E2 is independent of E3, and E1 is independent of E3. Then each one of these probabilities here are true if they're independent. Probability of E given at E1 given at E2 is probability of E1. Probability of E3 given E2 is probability of E3, and so forth. Therefore, we want to know what's the probability of all three of them. Then if they're all independent of one another, we just simply multiply the three probabilities. I'll show you an example of that in the textbook. And then if we have K independent events, K indicating maybe there are 10, K is 10. There could be 10 events that are independent of one another. Again, the probability of all of them happening simultaneously would be we just multiply the 10 probabilities together. if they are all independent. If they're not independent, it gets very, very complicated. We'll never ask that question. But it would look something like this, where the upside down U indicates and or intersect. They're all independent, then we simply multiply all of their probabilities. All right? All right, this is actually a good example. Let's look at this example here. Suppose a desktop computer system consists of a monitor, a mouse, a keyboard, and the computer processor itself, and storage devices such as disk drives. Most computer system problems due to manufacturing defects occur soon in the system's lifetime. So you purchase a new computer system and you're advised to turn the computers on as they are purchased and then let them run for a few hours to see if there's any problems. So we have different possible problems. We could have that the monitor is defective. You can have it could be the mouse is defective, the disk drive, when they used to have, well, they have disk drives that are internal now, but the disk drives could be defective. The processor, the computer processor is defective. Now, each of these events are saying they're not defective, all right? So you have to be careful in reading this. So these are the events that these particular items in the computer are not defective. All right, suppose the probability that E1 and E2 are defective, each of the are not defective, is 0.98. All right, there's a 98% chance that the monitor is not defective. There's a 98% chance that the mouse is not defective. There's a 95% chance that the disk drive is not defective, and then there's a 99% chance that the processor is not defective. Okay, so those are the 4 probabilities. We want to know, let's say it says here, the probability that all these components are not defective and the system will operate properly is therefore what? Well, the only way the system operates properly is that all 4 of those things are working well, they're not defective, and we just simply multiply the 4 probabilities. All right, so it's 0.98 times 0.98 times 0.95 times 0.99. Obviously, you need a calculator to be able to answer that question. The answer is 0.89, 89% chance that when you get the computer, it's gonna work properly. Okay. Now, what if you wanted to know the following? What's the probability that all the components are working properly except for the monitor? Well, the monitor is E1 working properly, so the probability that it's not working properly would be the complement of E1. That's 1 minus the probability of E1. Remember, the complement is going to be 1 minus the probability. The probability of an event, and then that's PE1, that's for the monitor, and the probability that, and that means the probability it's functioning properly. Probability that it's defective is 1 minus that. So that was 0.98 for E1. The probability of E1 is 0.98. 1 minus it's 0.02. Probability that the other 3 are working is just, again, you multiply those 3 probabilities, 0.98, 0.94, 0.99. So the probability that all the components except the monitor will be running properly is 0.018. Small probability, just 1.8% chance of that happening. Okay. Notice we can do this because if these components are independent of one another, if these events are independent of one another, the complements are also independent. That's why we can multiply the complement also. And then, of course, this was one of the questions on the test about sampling with replacement, sampling without replacement. What is sampling with replacement and sampling without replacement? Sampling with replacement means what? Means that once we select an item or a person from for a sample, then we put them back. We put them back. You know, that question about the urn, right, with different colored balls. If we select one of the balls, it's red, and then we're ready to select another ball. Well, if the number of balls in the urn remain the same, that means that the red ball had to be put back into the urn for it to be the same as before. So that's called sampling with replacement. In surveys, we do sampling without replacement. Why? Because once we interview somebody for a sample, we're not going to re-interview them. So they're going to be left out of the sample. Now, one of the things that we want when we ever do sampling is we want to make sure that we want to make sure the probability of being selected for the sample remains the same. So sampling with replacement, the probabilities remain the same. Sampling without replacement, they don't. That's a problem. All right. Again, here are the definitions here. Okay. So it is important to know. So the question is, how can we? It doesn't mention it here, but how can we be sure that our sampling probabilities don't change too much? Well, one of the ways of making sure of this is to make sure that the population is large relative to the sample. Population is large relative to sample. So when you do sampling without replacement and the probabilities change for sampling for somebody, they don't change by very much. All right, they change very little. And that's really why we can assume sampling with replacement when we do sampling, even though it's really sampling without replacement, because the probabilities don't change very much. All right, so this is, they want to show you in this example here of what sampling with replacement and sampling without replacement will lead to if we're dealing with much smaller population. That is, with, let's say, with playing cards. All right. So suppose we want to select 3 cards from a standard deck of playing cards, and we shuffle them, right? And then we select the 3 cards. That's one way of doing it. So if we select the 3 cards out of the deck and we don't put them back, that's called sampling without replacement. If we actually put them back in the deck and then reshuffle and select 3 cards again, that's called sampling with replacement. But of course, in card games, we don't do that, right? We do sampling without replacement. All right. So again, suppose we are selecting the 3 cards, and suppose H1 is the event that the first card is a heart. H2 is the event that the second card is a heart. Third event is that the third card is a heart. As you know, there are 4 suits in a deck of playing cards, so heart is one of the suits. All right. It says for sampling with replacement, the probability of H3, what is H3 again? That the third card is a heart is what? It's 1/4. There's 4 suits, right? So if every time we select a card, we put it back into the deck, the probability that the third card is a heart will remain 1/4 because there's 4 suits. And it doesn't matter what happened in the first 2 cards that are selected, right? Because they were put back into the deck. So for H1, for the first card selected, for the second card selected, for the third card selected, always going to be a 1/4 probability of selecting a heart if you just put the card right back after you selected it. However, the probability of that third card being a heart will be different if you don't replace the cards in the deck after you selected the first 2 cards. Probability of heart will be different because of, number one, there would be fewer cards in the deck, right? If you don't put them back, by the time you get to the third card, how many cards are there in the deck? Well, if you start off with 52 cards, you end up with 50 cards. Because the first 2 cards have been selected, they're not being put back in the deck. So we have 50 cards now. And then the probability of selecting the heart on the third card depends on whether you selected a heart on the first card and whether you selected a heart on the second card. So we would say, in this case, that sampling without replacement means that the probability of H3, the probability of selecting a heart on the third try, is dependent on what happened on the first 2 cards being drawn, doesn't it? It depends on whether a red card was chosen on the first card and whether a red card or excuse me, a heart was chosen in the first card, or a heart was chosen in the second card. So those events are dependent. Sampling with replacement, the probabilities don't change. It doesn't. So the probability that you selected a heart on the first try makes no difference to whether you select a heart on the third card, because you put the cards back. The probabilities didn't change. So sampling with replacement leads to independent events. Sampling without replacement leads to dependent events. That's what's really what we're trying. That's the purpose of this little exercise here. So you should write that down. Make sure you understand that basic concept. Sampling with replacement, independence. Sampling without replacement, dependence. Okay? You should know that basic idea. Okay? All right, this looks like it's getting a little complicated here, but as you can see, what's the probability, for example, of the third card being a heart if the first two cards were hearts? That's what it's saying here. This probability here. Well, if we started off, how many hearts are there in a card? If 1/4 of the cards are hearts at the beginning, that's 13 cards are hearts. 1/4 of 52 is 13. If the first two cards are hearts, that means we're left with 11 hearts in the deck out of 50 cards. So that's the probability that the third card will be a heart given the first two are hearts. Now, what's the probability of a heart, the third card being a heart, if neither one of the first two cards were hearts? Well, that means we still have 13 hearts in the deck out of 50. This is the probability of 0.26. Now, all of this is assuming sampling without replacement. We see the probabilities change depending on what happened before. These are dependent events. Okay? And that's what they're trying to bring out with these events are dependent, not independent. Now, here's the point I was making earlier in the slide here, that if the sample size, we're actually doing a survey or an experiment, and we're acquiring people for our study, and we're doing a random sample, either simple random sampling, cluster sampling, stratified sampling, systematic sampling, whatever it might be. We have a sample size of n, which is maybe 100, could be 100, could be whatever. It's selected from a population of big N. So the population size, we're mentioning big N. So suppose we're selecting 100 people out of 1 million people. So small n is 100, big N is 1 million. It says the probabilities of successive selections calculated on the basis of sampling with replacement and on the basis of sampling without replacement are nearly equal if n is small compared to n. Now, that sounds kind of complicated wording there, but what they're really saying is that if the sample size is small relative to the population size, typically here in this book, they see 5%. The sample size is no more than 5% of the sample size, of the population size. Right? No more than 5%. Then we can assume independence when there really isn't independence. The probabilities are not going to change very much if we simply survey people and then not put them back into the population to be sampled again. Okay, so we can do surveys, we can do sampling, and we can assume independence, assume sampling with replacement, because the probabilities are not going to change very much. We can just make those assumptions. So this slide here is extremely important, because without this knowledge here on this slide here, we wouldn't be able to do the statistics that we're going to learn later on. All right, because the statistics that we're going to learn later on assume sampling with replacement and independence. And in reality, that's not what we're really doing in real life. We're doing sampling without replacement, and we really have dependent situations. But as long as we keep the sample size small relative to the population size, we can make the assumption of independence, make the assumption of some sampling with replacement, because the probabilities don't change very much. All right. Very important slide, typically tested on in the final exam, but in a very general way. It's tested on. Okay, any questions about this 6.5? Okay, look at 6.6. All right. Now, here is another rule called the addition rule. We wanted to know what's the probability of one event or another event occurring. What it's saying to do here is it says we want to add their probabilities, then we want to subtract the probability that they're occurring together. Well, that seems kind of strange, right? Why would we want to do that? See if they have anything here that would help. Let me see if the slides have anything. Doesn't seem like they do. But how do we understand this? Well, if two events are occurring, it is possible that both events occur simultaneously. All right? It's possible. It's possible. If they are what? If they are independent, right? If they're independent, they certainly will occur. They can occur simultaneously. But even if they're dependent, they can occur simultaneously. But it is possible that two events can occur simultaneously. So that means that when we calculate the probability of E, the event E, it includes that possibility that E and F occur simultaneously. Same thing with the probability of F. That would include the possibility that they're occurring together, E and F. So when we add probability of E and probability of F together, we're double counting the possibility of them occurring simultaneously. So what do? We subtract one of those events that they occur together. So we're double counting the probability of E and F occurring together, but they're built within each of these two probabilities, and then we subtract one of them to remove the double counting. Now, if E and F are mutually exclusive, if you remember that from last time, maybe you don't, what does that mean? That means E and F cannot occur simultaneously. Okay? It can't occur simultaneously. It's like, what's the probability of you getting a C in this course or a D? Well, you can't get both a C and a D. So those two events of getting a C in the course or a D in the course are mutually exclusive. They can't occur simultaneously. So which means that this probability here, the probability of E and F occurring together, would be 0. So if they're mutually exclusive, this subtraction here is not unnecessary because the probability of E and F is 0. And therefore, you just simply add the two probabilities together. So that's the key here. If the two events are mutually exclusive, we simply add the two probabilities. Okay, when we say or, probability of E with probability of E or the probability of F. All right. So, see an example of this. Suppose 60% of all customers of a large cable company subscribe to internet, 40% to phone, 25% have both types of services. 60% of the customers subscribe to internet and 40% subscribe to phone service. Let me ask you something. It says 25% have both types of services. All right. Let's read through this. We wanted to find the following events. E is the event that a selected the customer has internet, and F is the event that the person has phone service. All right. All right, so this is the information we're given. We're also given the information that there are 25% of the people have both. What's the probability of having either phone service or internet? Internet is E, and I guess phone service is F, right? Probability that if you select a person at random, they have one of those two types. Well, if you add the two probabilities, you get 0.6 plus 0.4, which is 1, which is 100%. But then you have to subtract the probability that they have both. Because there's nothing in this problem that says that E and F are mutually exclusive. It is possible, isn't it, that a person has both internet and phone service. They have both with this company. They're not mutually exclusive. Therefore, you have to subtract the probability of both. So when we add the two and subtract the probability of both together, we get 0.75. There's a 75% chance that if we select a customer at random, they're going to have either cable or internet. Now, what is this telling you? There must be more than two types of services, right? Customer, right? They have at least one of these two types. There's only a 75% chance. That means there's a 25% chance that there are more types of services. The event that the customer has neither type of service would be 25%. That's what I just said. So E, and this is the way you would write it here. E union F means internet or telephone. And if the person has neither one of them, would be not E or F. So it would be 1 minus that, which is 0.25. 1 minus what? 0.75. How do you represent all of this, these type of problems? You use what's called a Venn diagram. Venn diagram. So the probability that you have at least one means that you either have one or the other or both. Does that make sense? At least one means one, the internet, the telephone, or both. Now, the circle on the left here, this circle here could be the internet. The circle on the right could be telephone. And what's in the middle here, where they intersect, they have both. Okay? So this representation here, where you're coloring in both balls with both circles here, means either one or the other, and another way of saying it, at least one. So either internet or telephone, which means at least one of them. It's everything within the two circles. What if we had this? What's the one that what does this represent? This one right here in the middle here. Well, this is saying the blue here is internet only. The tan on the right here is telephone only. What's in the middle is left out. So this is saying exactly one of the services. So this in the middle here represents exactly one of the services, either only internet or only telephone, but not both. It's the one in the middle, the area in the middle is not colored. Here, notice it's only the one in the middle that's colored, so this would be the case of internet and telephone would be in the middle here. Notice if you do the union of these two, you get 4. E union F. Okay. Any questions about that? The Venn diagrams are very useful for doing problems like this. Okay. So what's the probability of getting exactly one of them? Exactly one of them. How would we figure that out? Well, we would figure out the union of the two, which is 0.75, and then we subtract what's in the middle. Now you might say to yourself, wait a minute, didn't we already subtract to get the 0.75? We go back, let's see if I can find that here. Yeah, did we already subtract it once to get the 0.75? Isn't that the E or F? Well, yeah, because what we eliminated here is the double counting. Here, we're eliminating not only the double counting, we're eliminating what's in the middle totally. Okay. In other words, this is the answer we're looking for right here. It's in the middle here. It's either one or the other, but not both. That's what the answer is here, which was 0.5. What's the probability of getting exactly one of them? In other words, either internet or telephone, but not both. It's 0.5. And then they have this really fancy formula here for all three. I do have a problem that I will show you. Probably have to show you next time, which will use a Venn diagram to answer that question without using this formula. Because this is, now you could use this formula, by the way. You can use it, but it's only going to answer one of the questions, which is what's the probability of E or F or G if you have three events. Right? And you would have to be given all this rest of this information on the right to be able to plug it in. It's easier to do it the way I will show it to you, which will be just a logical way of coming up with the answer. And I'll show it to you that probably next time. All right. Now remember last time, remember a minute ago, we talked about this. This is the general addition formula here. That was the general addition formula. And I think the slide out actually made a mistake here. So I'm going to have to change this. The publisher put this slide out, and this is incorrect. This is not the multiplication rule. Obviously, this is the addition rule we just saw. So where is the multiplication rule? All right. It's in the previous. Let's stop sharing for a minute. Let's see if I can find it in the previous slides. Go back to this one here. See if I can find it. Multiplication rule. Right here. Second. I apologize for that. That slide is obviously needs to be changed. All right, just give me a second. Here it is. This is the slide. This is section 6.5, the previous section slides. And this is slide number, if you were going to go through the slide number 11. Remember, this is the formula for conditional probability. And then if we multiply both sides, we get the multiplication rule. This here in the middle is the multiplication rule. It says the probability of E and F is equal to the probability of E given F times the probability of F. Now, I had mentioned to you that there are two sets of these. We could say the probability of E and F is also equal to the probability of F given E times the probability of E. There's two sets of multiplication rule. All right, back to where we were. Okay, so this here is wrong. This thing here, that's the addition rule, so that's a mistake. So they're going to use the multiplication rule we just came up with. All right, so it says here, suppose that 20% of all teenage drivers in a certain county receive a citation for a moving violation. That means 80% receive a citation. Now, it also says that suppose that 80% of those receiving such a citation attended traffic school. All right, so 20% of teenage drivers got a citation for a moving violation. And out of those who did get the citation, 80% had to attend traffic school so that the citation would not appear in their driving record. Okay. It says here, if a teenage driver from the county is randomly selected, what's the probability that he or she receives a citation and attended traffic school? Well, the 20% here is an unconditional probability. It's a probability that a teenager got a citation. But the 80% number up here is a conditional probability. It's the probability of attending traffic school given that they got a citation. All right, so let E be the probability that the driver attended traffic school, let F be the probability that they received a citation. So what they're asking for in this, what they're giving you in this problem is the probability that the person attended traffic school given that they have a citation. That's the 80% right here. See it? The probability of E that they attended traffic school given that we know that they received a citation. Probability of F is 20%. That's for anybody who of receiving a citation. 20% probability of receiving in general. So what's the probability of a person receiving a citation and going to traffic school? It's the product of these two probabilities, the conditional probability and the unconditional probability. This is the multiplication rule. Now, E and F is assumed here. E and F are not independent. They're dependent. So when we multiply these two numbers, we get 0.16, which means that 16% of all teenage drivers received a citation and attended traffic school. So if we selected a teenage driver at random from the county, what's the probability that they received a citation and attended traffic school? The answer is 0.16. Any questions about that? This is a general multiplication rule. And this is way too complicated for you guys, so we're going to skip that. And we will skip that example. So just know that this example that you're seeing here, not the traffic school example, but this one here, starting with general multiplication rule, and this one about the passengers and all, this is a little too complicated. I will not test you on that, all right? So I'll never give you one where there's dependence and there's 3 events. I'm not going to give you anything that looks like that. So don't worry about that. There's also what's called the law of total probability. Now, suppose that there is an event E, all right? There's some event, and it can occur only under 2 circumstances, either with another event B1 or another event, a second event B2, all right? So in other words, when you have the event E, it can either occur along with event B1 or with B2, but not with B1 and B2. So B1 and B2 are mutually exclusive. So the probability of E is equal to the probability of E and B1, or it's either plus the probability of E and B2. So E can only occur with B1 or with B2, and that's it. It can't occur under any other circumstances. This is called the law of total probability. Probability of E occurs either with B1 or E occurs either with B1 or B2. Now what they're doing here, and this is a little complicated, is that they're replacing this with the multiplication rule, right? They're saying probability of E is equal to this probability, E and B1, which is equal to E given B1 times the probability of B1 plus E given B2 times probability of B2, all right? I will probably not give you a question with the law of total probability, but it may come in handy later on, all right? It's just something to know. But it requires that E occurs with either B1 or B2. All right, so a little bit complicated. Again, looks very complicated here. I will not give you any examples like that. All right, so don't worry about that. I'm just showing you this. Yeah, I'm not even going to go through this. All right, little too complicated. All right, and then finally, Yeah. So everything here, and then this next section on Bayes' rule definitely will not be tested on. It looks really gruesome. It's really not, but it is gruesome for many introductory students, and I will not test you on Bayes' rule. All right. So just know that in section 6, the only thing that I will be testing you on in this section here are 2 rules: general addition rule, that rule, and then the general multiplication rule, which is which again, there's a mistake in the slides here. I will change that, and I will correct it and post the correct multiplication rule. But that is the multiplication rule that was brought out in section 6.5. All right. So those are the only 2 rules you need to know in 6.6, and everything else in here, it's law of total probability and the Bayes rule and all that stuff, all that rest of the stuff in this section, you do not need to know. All right. Because it's really not required for the course, and the introductory course will not require any of those things. All right, so that is it. We're right at 1:45. So even with the late start, it looks like we're done right on time. The best way to learn this chapter 6 is the examples. And what I'm going to do, I already picked out the examples. I will show those to you next time. Now, I will not post them. I will show them on the video and show you in general how to solve them, and they will be your homework. All right. So I'm actually going to be displaying the homework and showing you the general ways of solving them next time. They will be the homework. So you'll just by watching the video and then redoing this in the homework, and you'll get a grade for it, hopefully a very good grade. Again, I'll be showing you how to do each one of the problems. So that will be for the first half of Wednesday's meeting, and then we'll start chapter 7 right after that. All right. So that homework that I'll be showing you how to do will be due next Monday. All right. But please watch the video. Make sure you know how to use your calculator. All right. That's very important that you're familiar with all the steps to solve these problems with your calculator, so that when you get tested in the future, you're not going to be surprised by how to solve something, and you know how to use your calculator. I have a feeling that some people in this last test were using their calculator for some of these questions for the very first time. All right, not a great idea in a test to do that. Any questions? Any comments? No, nothing? All right, I'll stop the recording and I'll see you guys on Wednesday.
Have a good one, Professor.
You too. Take care.
Have a good one.
Thank you, Professor.
Thank you.
You're welcome. Take care.